Thanks, guys. For those of you who hated me yesterday, sorry about that. I have the, is this the one for today? Great.
Yeah.
I did this morning. I really wanted to share with the data scientists among you some stuff, right? Can I have a timer on, please? Great. 20 minutes, that's what I got. Okay, so I wanted, this is a bit nerdy, right? I'm gonna out-nerd Tanaka-san from yesterday, right? So, for, you know, hopefully you'll like it, right? It's all drawn, because I did it this morning. Unconventional stories, that's what it was originally gonna be called. I want to share with you some thoughts about how algorithms are not very important. Okay, this is a sort of a slide from yesterday. Pie chart, you all hate pie charts. The amount of time you do preparing data, the amount of time, it's like 90% of time preparing data, 10% of time doing your algorithm. We all kind of nod on that. And the problem I have with that is that if you do that, you're limited by the algorithm you choose and the data you choose, and unless you combine that with imagination and modeling, right? Unless you think about the world, right, and try and model that and imagine the data in that sense, and perhaps you'll see a little bit more what I mean by that. You'll just be limited by a set of algorithms you can pull off some Python library, you know, scikit-learn or something, and you won't know which bits of the data to choose, and you just kind of get what everyone else gets whenever they run this thing. And that's got worse recently because a whole load of vendors out there are telling you that data scientists are not very important because you've got some kind of automatic feature selection thing, and you've got grid search, and you can just be a moron, right? You can just kind of press a button and something will come out. And again, it's all very well having automatic feature selection, but if you're then limited to the features you put in the structure that you give them, right? So features are not just columns in a table. You can think about features in lots of different ways, right? And grid search is all very well, but you can only search over the grid you've got, and grid search is not scalable, right? If you've got 1 billion rows, right, and 15 dimensions, right, good luck on you. Okay, this is the most boring data set in the world. I'm going to do a bunch of things with this data set, right? This is a data set out of a bank, a bunch of buyers and sellers, shops and people, time they did it, the amount of money they spent in euros or pounds, whichever you choose, and you can see that the shops, we've kind of got a location for those shops. This is a log, right? It's just one thing after another, right? It's just a log, right? What can you do with this thing? This is the most boring data set in the world. And most people, given a data science problem, will go, oh, I'll aggregate it. I'll turn it into a big old table of features. I'll chuck it into random forests, and then I'll chuck it into logistic regression, and then I'll chuck it into a neural network, and then I'll do a grid search. When I say most people, none of you would do this, I'm sure. But a moron would, right? And there are plenty of them out there. So I'm going to show you a number of different things that have nothing to do with algorithms and are transformative and result from a deeper understanding of data and modeling the world. First topic is abstraction. So we had a product at Barclays. It was a cool product. We took this data that I showed you, this kind of thing, and for businesses in the UK, we were able to do a bunch of graphs about how they were performing, how much they were spending on electricity over time, and when their customers returned to them, that kind of stuff. And we gave them a dashboard, and we found out the amazing insight that a hairdresser in South London is not a statistician. And couldn't make head or tail of this thing, right? Graphs, I know how to cut hair, I don't know what to do with these. So we wanted to turn that into just sort of statements. You need to know this. You are spending too much on electricity. Your competitors are doing much better in customer retention than you are. We wanted insights. We wanted advice. Now, if advice is not a data science product, right? I don't mean chatbots. That's just pretending to be a person. This is actually what you're going to tell them, right? If advice isn't data science, I don't know what is, right? We need to, but in order to do this thing, I'm going to this is going to be a fairly superficial talk, I'm sorry. In order to do this, we needed to move from examples, instances of insights, into the idea of insight in general, right? What is insight? What do we mean when we've said something insightful, right? It's not necessarily clear. This is where the data scientist is able to apply their imagination. So in some sense, you could just do a whole load of SQL queries, right? As it turns out in this problem, we had about 1 billion rows. We thought to about 1,000 SQL queries, each of which would take about 5 hours on Hive or Impala, which is the Cloudera big data query engine. It's going to be about 5,000 hours. That's quite a lot of processing time. And what's more, we had to do each of these SQL queries about 250 lines long for one reason or another. So the chance of getting huge errors were a problem. So I want to give you 3 levels of abstraction we applied to this problem, right? How can we take this problem of wanting to kind of tell people what's going on, right, but doing it in some kind of abstract way so we can apply it and process it? This is real data science. We did this, and it's not to do with random forests. Okay, first thing, what is an insight? That's a level of abstraction. It's actually a massive level of abstraction. What is insightful? People gave me people, oh, well, it's something insightful in it. We came down to an abstraction, which is an insight is a triple of a statistic, a contextual statistic, and some kind of relevance score, which tells you which insight I should be telling people, right? Now, I'm not going to go into, you can think about this thing. I hope what you're looking at it is saying, that is really oversimplistic. Now, if you think about it again for the next few hours, right, you'll find that that is actually quite profound. And it really works. It's very, very interesting how much value you can get out of that level of abstraction. Secondly, when we start thinking about calculating statistics, we're thinking about applying functions to sets of data, right? Actually, yeah, sequences of data in this case, okay? It turns out that all the kind of functions you do in SQL, right, can be reduced to a few functional forms, right? A relatively few functional forms, which are all combinations of 3 things: aggregators, filters, and combinators, right? So there's mathematicians out there, right? You're leaving behind just kind of, oh, well, we play around with computers and we download some stuff. You're actually thinking about fundamentally what is at the core of a SQL query. Because once you understand that you can have aggregators, filters, and combinators, you can actually then start expressing those SQL queries very, very profoundly and parsimoniously, so you don't need to be dealing with 1,250-line queries. We kind of got it down to each query was about 3 lines of Scala, right? So you're much, much simpler, right? And because you can abstract away, you're then only thinking about certain patterns that you're applying. If you think this is computer science, you're right. If you think it is data science, you are also right. Thirdly, this is perhaps more for the big data guys between you. If you think about your aggregators and abstract them away to monoidal operators, right? Some of you will know what that is and some of you won't, right? A monoid, you can go and look it out. It's an operator that's a closed set. So you aggregate with a monoidal operator, you produce a monoid. There's all sorts of important things around that you will need to understand if you do big data, right? You will need to understand if you do big data. Why is that? Because if you compose monoids together, I know I'm out nerding Tanaka, right? I hope. If you do that, you end up being able to do all these queries in a single pass of the data set because you're using monoids, because you're abstracting away. Single pass of the data set. When you think that the main issue with processing, and big data processing in particular, is network latency. Right, the time it takes to get data from one place to another in the network, right? Doing it in a single pass means you only move stuff once, right, until you do your reduce, right? So we've got 3 levels of abstraction, right? This may be a little foreign to you. What I'm trying to say to you is that we move from 5,000 hours to 3 hours, right? And what's more, it's better than linearly scalable. In other words, we could do this, so we not only took the step to understand what insight was, right, in a generalized sense, but we were able to process it extremely quickly and express it extremely parsimoniously. This is the kind of thing that the only person in your organization who can do is you, the data scientist. This is where you're adding value. Secondly, for those of you who are still alive, sorry about that, I wanted to think about networks. Right? So you see our boring data set on the right-hand side. Right? It's just a log. It's just a log. It's just one thing after another. Am I still on? Good. So, again, those of you who are a bit thick, switch on your imagination and think about that data set. Right? What is a set of pairs? A set of pairs is a bipartite graph. Right? So we all talk about graphs and networks and all that, but fundamentally, a graph is just pairs of nodes, right, with edges between them. Right? But we all know, because of Facebook and Twitter, that suddenly that edge and that different structure of data can give you an enormous amount of rich detail that you don't get if you just list stuff out. And because buyers and sellers are different kinds of things, we've got a bipartite graph there. Now, I'm going to kind of scud over this. This is a kind of an hour presentation in itself, just this thing we did at Strata last year. Strata's the Hadoop thing. But the point here is that if you are interested in understanding the relationship between buyers or the relationship between sellers, you can encapsulate that in the way that they link to each other through an intermediary, which in each case is either the buyer or the seller, the opposite thing, right? So Tesco is related to Aldi in some sense through the customers it shares, right? Now, you all know what this is. This is like a distance metric. This is like a cosine rule, whatever, cosine similarity, right? Except cosine similarity doesn't deal with sparse networks, right? When you hardly have any overlap, it's no use at all, right? The other problem with shopping networks, if you use like a conventional graph metric, is that it doesn't deal with hubs. So if everyone's connected to everyone else by the local supermarket, right, everything's either one step away or 2 steps away. Very hard to understand how connected one shop is to another in these instances. We thought of a thought experiment, right? So we've done a first step. Maybe you think of it as a step of abstraction, right? Set of pairs is a bipartite graph. And then we thought, okay, here's a thought experiment. Imagine, this is another set of imagination. Imagine I have a red paddle or something. I've drawn it as a balloon, but it's kind of a red paddle. And I want to know how close Tesco, which is the shop at the top, is to Aldi at the bottom. If I take my red paddle, this is a thought experiment, remember, and I just take a bunch of them and I give them to a random person in Tesco and mark the paddle. And then I say, when next shop you go to, give it to some other random person and mark the paddle again. And tell them to pass it on and pass it on and pass it on. And I'm going to go and wait at Aldi, wait for the red paddles to walk in the door, count the number of marks on that paddle and do some kind of average, right? This is suddenly giving me, right, this step of imagination is giving me, in some sense, the distance between those two shops using the entire network, right, using the information from the complete graph. Don't ask me how to calculate it. That's another hour's worth, right? But the point is here, steps in imagination. If you simply took that list, right, and did a cosine similarity with your recommender, whatever it is, you'd get nothing out of that because hubs and sparsity. Yet this is incredibly powerful, right? Particularly because it then allows us to partition networks in preference space, right? So partitioning is a key part of what you do, right? When you have to deal with all the data at one time, you can't do it, right? So you have to partition your data up into little bits, particularly when you're dealing with big data. When people partition, they partition on things they can see, things they can think about. What we really want to do, for example, when we're thinking about people's preferences for shops, is partition in preference space. Move your brain out. Start thinking in spaces that you can't see, you can't touch, right? But relate to the core principle at hand. Sequence and location. Here's an example. I want to know where some certain shops are, and I know where some of the shops in my boring data are, but I don't know where the other shops are. Right? And you look at it and you go, oh, how am I going to do this? Because I just don't know where Tesco is. That is, of course, if you're reading across the data. Read down the data, you suddenly got a sequence of shopping events. Think about how people shop, right? Data is not just stuff in a computer, it's generated by people doing stuff very often. So what are people doing to generate this data? They're going on shopping trips. I go to a hairdresser, I go to Tesco, I go to the bookshop, I go to the coffee shop. I do shopping trips. And if they're short distance in time apart, I can assume that if I know where the hairdresser is and I know where the bookshop is, but I don't know where Tesco is, Tesco's kind of be somewhere pretty close to the places where I know, right? And you can start thinking in terms of sequences, right? What have we done here? We've taken something that looks cross-sectional and gone, hey, I can imagine this as a sequence of people doing stuff, right? One thing after another, right? And that actually has a geolocational element, right? It's not explicit there, right, is it? You just happen to know that Tesco exists in a certain place, and you know that people exist in a certain place, right? We're not quantum people. We have a place that we are, at least statistically speaking, right? And using your imagination to go beyond just what this data says, right, into what is this data? What's not written down in this data set? Second thing around that, we want to be starting to partition stuff. I want you to think as computer scientists as well as data scientists. It's all the same thing, by the way. Because when you start, imagine you wanted to find how the nearest neighbor. You want to do nearest neighbors? Great. Let's do nearest neighbors between 2 million different things. So you've got a Cartesian product, and you're going to be looking at, what is it, 2 trillion, is it 2 trillion comparisons, right? Good luck, right? But these are the kind of data sets people use, right? And these kind of searches are really, really important. So you want to be thinking about a KD tree, or you can see here drawn a VP tree, right? Tree structures, n log n complexity to build, log n to query, right? These are the kind of things that if all you care about is scikit-learn, and you know, good luck doing a grid search. Even if you do that, actually, but good luck doing a grid search if you haven't done that. Use your imagination to think more deeply about what it is you're engaging with. Really quickly, I'm sorry I've gone over, grammar of events. So again, you look at these transactions down here. What do they signify? They signify big events in people's lives, maybe, right? So people buy a car. Maybe that shows they've got a job, right? People buy a car and and have a baby. Maybe the combination of those two things mean they're moving house. Right? I think that's a will, when people die, a will, that kind of stuff. They signify that kind of thing. Now, the interesting thing is, if you were just thinking about feature selection, you would think of those things independently. But there's a grammar to these things. People combine what they do in a way that's actually very similar to language. And we extracted events, that's quite straightforward at Barclays, and then applied NLP technology to it. Right? So we thought of sequences of events as a very limited vocabulary language. As a result, we found 750 million quid for the bank. Other hidden meaning, right? Think about hierarchies, right? You don't always see hierarchies naturally in data. It's not always explicit for you, but that's extra information for you if you can think about hierarchies. Think about hypersurfaces. Things are related to one another, right? They have distance to one another. We use that in terms of loans really successfully, non-parametrically as well, really important. Distributions, Bayesian, anything Bayesian, right, where you have to combine expert opinion and data, and you have to do it in a kind of in a way that allows you to understand the world, right? That's not going to come out of some library, right? You're not going to stumble across that thing. You've got to think what is going on here. So, conclusion. 90% of the value of data scientists adds from problem structuring and modeling. I made the 90% up, by the way. Everyone makes these numbers up. I don't believe any of these numbers, right? And imagination, right? Imagination. Don't just look at the data that I showed you, the most boring data set in the world, and say it's boring, right? Because it's all the stuff between the lines that makes you a data scientist. Thank you very much.